No, no, no. Yeah. Good morning, everyone. Good morning. Thank you for being here. So it's my pleasure to introduce our fourth lecture series, our fourth mini course. Sergei Gukov will be teaching us about BPS Q series invariants of free math.
Oh, thank you very much. Thanks all for coming. It's early morning. Thank you for waking up. So this will be a course or mini course about several topics. So most prominently, three-dimensional topological point of view theory or invariance of knots and free manifolds. It also will be interactive. I'll ask you to do some homework, solve problems, and sometimes ask questions. So how many of you like knots and free manifolds? You can be honest. Don't have to raise your hand. But luckily, not everybody raised their hand, but luckily that's not the only topic. So there will be three things. So first I'll give you a big picture. So in addition, we'll talk about quantum groups. Quantum groups. So usually these are denoted as UQ of some root system or Lie algebra. So this script or German G for me most of the time will be SL2, but those of you who are interested in representation theory may also ask what happens if this is E8, E6, or even more exotic types. How many of you have heard about quantum groups? Okay, that's perfect. Really. So then another subject that we'll touch is subject of infinite dimensional algebras. Well, in some sense, quantum groups belong there, but what I mean by that is that there is something even bigger, algebras which are much larger. And I'll just put them under the name of vertex algebras. And these two are also related. So relation between these two is very deep and is sometimes referred as Cartan-Lustig correspondence. So Cartan and Lustig did lots of interesting things, and there are many things that could be called Cartan-Lustig correspondence. Many of those are actually maps which are not quite bijective, whereas the word correspondence suggests something sort of bijective. We'll talk about to what extent and how. And that's going to be the one closer to us. If you never heard about this, that's cool because I'll basically give you some introduction relevant to our topic. So one thing that will appear throughout every single lecture, from the quantum group point of view, there is this parameter Q, which for us will be generic, and this is really important. So it will be, so this whole lecture series is sort of based on this premise that Q will be inside the unit disk. So very often, if you had advanced quantum topology course, you want to specialize this to be a root of unity for reasons which will come up and we'll discuss at length. But for us, what's important is that every time you see Q on the board, and I promise you, you will see Q a lot in this lecture series, that refers to generic parameter of quantum group. And again, we'll take it to be inside the unit disk. So by charting this roadmap, I'm also sort of introducing notation, setting up the state. And before we jump into the subject, you can ask, okay, what are the benefits? What am I gonna learn from this? You'll learn from this a couple of things. So for instance, there is a very traditional relation between quantum groups, vertex algebras, and 3D QFTs, where if you study knots and links,
it might be good to use the other board, the unmovable board
on the bottom.
Yeah, pull up the board from the bottom.
All right. Oh, I see this one. Yeah, this one. See, I'm also learning, so we're all here to learn. So, right, if you have something three-dimensional, the most interesting process in three-dimensional topology is braiding. So illustrated here, you have some set of lines. You can think of this as pieces or strands of a knot or link, and they braid. And connection to vertex algebras or vertex operators arises if you try to slice your three-dimensional space by something two-dimensional. And on this two-dimensional slice, these lines or strands may naturally end at various points, and this would be vertex operator. So two-dimensional slice is where the vertex operator algebra lives, and this is three-dimensional, I'll probably call it bulk, because it's like bulky part of the space, where quantum groups and three-dimensional TQFTs live. And this is very traditional picture. I won't need it in any way. Again, this is just sort of appetizer jumping way ahead into this lecture course, but in fact, we won't even need it. But what will happen in this course is that there will be a picture of this sort, so we'll come back to it tangentially, but there will be completely new relations between vertex algebras and 3D TQFTs, which do not fit into this paradigm. So this paradigm goes back to essentially 80s, and its relation to three-dimensional TQFT is usually formalized by Toraev's theorem. So this is due to Toraev, which is link between the lower level and upper level, which says that if you give me a tensor category, or sometimes called modular tensor category, I can construct for you a TQFT. And this is certainly true. This is something that, again, we'll discuss. This is, again, appetizer jumping way ahead. That's based on Brzezinski-Toraev construction. Right, construction. But what we'll see in this course is completely new perspectives on, so my main goal will be sort of to focus on the TQFT aspect, talk about invariants of knots, three manifolds, how they fit together, how to cut and glue, and so on. And we'll be working with these objects as sort of secondary, but as a byproduct, what we'll see is that we actually will learn something new about quantum groups, and we learn something new about vertex algebras, even though that's not going to be the goal. The goal will be, the purpose is different, but the story will lead us to new perspectives on these older subjects, on quantum groups, and new perspectives on vertex algebras. So if it's okay, I'm going to abbreviate vertex algebras as VOAs, which is fairly common. So therefore, hopefully there is in this 4 lectures something that could be useful to everyone, depending on your main interest, whichever corner is closer to you, hopefully there will be something to discuss. Okay, so this was like appetizer or jumping again quite a bit ahead. I'll now start in a more systematic fashion. I don't know, but are there any either logistical or big picture questions? At any point, again, feel free to interrupt, ask questions. It's good.
I mean, sort of unrelated, so feel free to ignore. I was just wondering, is there any way to understand line operators in 3D TQFT as representations of something without considering boundaries? Or is that the only way we do it?
No, that's not the only way, and in some sense, I would say, considering, yeah, so that's in part gonna be some of the new perspectives. So indeed, you're absolutely right that this lines or strands in 3 dimensions better be thought of as representations. More precise statement is that I'll probably use this declaration lambda, meaning that this will be color in language of knot theory. For example, when we talk about color John's polynomial, it's actually colored by something. And this something typically is a representation of either quantum group or object similar to it. So that's going to be primary, and that's not really going to change much. But what will change is, in addition to this perspective, which is based on old paradigm, we'll have independent perspective on what this, for example, colors or objects are. But what set of labels, and therefore what set of lines one can consider. Any other questions? I don't have a plan to race to the finish line, so therefore, at any point, if we want to turn this into small discussion, I'm actually okay with it. I'll leave one. Okay, so then let's start. So this will be official start. That was kind of side or regression. So as I mentioned, most of my attention will be in this top corner. That's going to be the primary subject. And it's a bit hard to talk about knots, which are objects like this, or links, which are objects like this with several components, or 3 manifolds with their set up some stage. And this may be familiar, but I want to make sure that we all are on the same page. So I'll start with the theorem of Vickers and Wallace, which tells us how to build and classify 3 manifolds. So 3 manifolds are not terribly visual. These are some 3-dimensional bodies. And eventually my goal will be actually to move to 4-dimensional world. So the reason I'm doing all of this is because I care about smooth 4 manifolds. So we'll see how that comes about. And 3 manifolds and 4 manifolds are not terribly easy to visualize. So we usually try to reduce them to pictures of something we can draw on a board or a piece of paper. And that's where this theorem comes very handy, which says that every closed oriented connected 3 manifold arises by deforming an integral Bain surgery along a link in S. So what does it mean? It means that if you have a link, so here I'm drawing just a knot, which is a link with only one component. Imagine that, so already this planar diagram suggests that it's sort of seating in 3 dimensions. There is some thickness to it because I have overcrossings and undercrossings. So imagine indeed that this knot sits in 3-dimensional space, which is R3, or by 1 point compactification at infinity S3. So then we can take its tubular neighborhood. I'm not going to draw all of it. I'm just drawing a small chunk of it. It's going to be a torus for reasons that, again, we can probably quickly visualize. And the surgery, this iteration, means that you remove this tubular neighborhood from ambient space. So if you start with a three sphere where this object lives, you take S3 minus the neighborhood of your knot or linked K. So I'm gonna denote by capital K not strings. So this creates a manifold with a toral boundary, which is called knot complement, but then you glue it back. So basically you take, again, union with a solid torus, S1 cross D2, which is tubular neighborhood of your knot. But here you glue it back and you have a choice. So if you glue it back without doing anything, you obtain back a three sphere. But if you have here non-trivial diffeomorphism phi, which may not be connected to identity because the toral boundary has very large group of diffeomorphisms, in particular those which are not connected to identity are classified by SL2Z. So we have a choice of phi, which is element of SL2Z, 2 by 2 matrices with integer coefficients. And if we do that, then we can actually create what's called a surgery on K. It's usually denoted as follows, as 3 of K. So this indicates that our starting point is a three sphere or three-dimensional space. Again, think about this R3 with point at infinity headed, and K indicates a knot or a link on which we perform the surgery. So now, Bezout's theorem basically tells us that we can classify these elements of SL2Z by a rational number. So this phi effectively is a rational number, which most of the time I'll call P over R. So that's often called a surgery coefficient. And in general, the surgery is classified by such rational numbers. But this theorem says something stronger. It says that integral surgeries are good enough. So in other words, if you only limit yourself to those fractions which have R equals 1, these are relatively prime numbers, then you can access any three manifold. Any three manifold in the world can be obtained in this way. Okay. And I'll come back to why this is possible in a second, but are there any questions so far on notations or trying to unpack the statement of Licorice-Wallace? This is central theorem and three manifold topology.
Sorry, what's the data of phi in this function? S3K.
Right, so data phi, thank you for asking. I was going to report it here. So it's usually written as a subscript of this notation. So it would go in here, it would specify diffeomorphism. Since we agreed that in general, for a single component, this would be a rational number. For multiple components, it would be a rational number per each one. So we just label them by P over R. This would be notation here. So the whole thing would be specified by where we start and what we do the surgery and what are the surgery coefficients. That's right. Any other questions about notations, conventions?
Sorry, could you just remind me how we get the fractional numbers?
So this rational number in terms of, is SL2Z reasonably clear?
Yeah.
So SL2Z rises because once we excavate the tubular neighborhood, the boundary of the neighborhood itself and what remains is a two torus. So in fact, boundary of each piece here, this is a two torus and boundary of this is a usual two torus by mentioning T2. So now two torus has basis of cycles, let's say 0, 1, and 1, 0, right? And if you call this A and B, we're just represented in terms of this like integer vector notation with entry 0, 1, 1, 0. There is an actual action of SL2Z, 2 by 2 matrices with integer coefficients such that determinant is 1. So we can make this vector skewed, rotate them, but still the inner product is basically 1. So that's how SL2Z acts in the first place. So then it's a simple lemma to say that if you have PR something something, from this entries P and R, you can reconstruct both stars. That's how we get from SL2Z to a rational number. And then there is a further step, which is a statement in this theorem, which says that you can get from rational number to actually, you only need integers. So far, so good. Again, don't hesitate. This is central to all three manifold topologies. Right, so there are a couple of comments, remarks I should make. Maybe I'll just say remark and then leave it there. So this construction is highly non-unique. So just like you can construct knots and links using various diagrams, for example, this is what's usually called trefoil knot, but there are many other presentations of trefoil knot which have diagrams with 10 million crossings. And all of them, if they're representing the same three-dimensional object, they're related by so-called Reidemeister moves. So there are certain equivalences. So the way we build knots is highly non-unique, and Reidemeister moves are fairly known. Here, the analog is Kirby moves. So this theorem says that, yes, you can construct every three manifold you can dream of. For example, if the three torus is your favorite, there is a presentation like this. That's a good exercise to think what it should be. We'll get to it, and so on and so forth. But whatever your favorite manifold is, be it three torus or Poincare sphere or something like that, there are lots and lots of different ways of constructing it. And they're all related by Kirby moves. So this is something that I want to mention at this point, and we'll come back to how to use them in practice with hands-on approach in a little while. But it is second point where this comment is relevant is precisely the relation between working with the rational surgery coefficients and integral surgery coefficients. This actually goes into the proof of this theorem, where you can first, what you achieve is you show that you can construct any three manifold using rational surgery coefficients. And then using Kirby moves, you can simplify surgery coefficients at the cost of making your knot or link K more complicated. So in other words, there is this balance, and theorem says you can do this trade-off so that you can always achieve integral surgery coefficient. So that's it. Again, based on Kirby moves.
So you take such a knot and you make it way more complicated, but it's still the trefoil. You need to change the numbers that's associated to it.
Well, here you change both the numbers. Yeah, so the presentation of a manifold is labeled by the knot or link. So for instance, something like this would be, so here we have 17/5. This component could be minus. It doesn't have to be positive. 1/3, so that's very common. So this Kirby moves, what they do, they change both the link and the numbers, the surgery coefficients, in a compatible way, so that their whole thing doesn't change. Again, we'll see concrete examples very soon. Don't worry about it. That's why I'm not going to introduce them in detail. But what I want to point out is that those relations, those equivalences, are absolutely crucial to convert rational surgery coefficients, which is sort of generic, to integral ones, which are relevant to this theorem.
Why don't we need the framing of the thing?
These numbers are equivalent to give us the framing. So in some sense, actually they sometimes call framing coefficients. Surgery coefficients, framing coefficients, and
so do we have some canonical framing?
Well, it depends on perspective. So at this point, there is no need to introduce additional framing. So doesn't arise. So by framing, one can mean these numbers, but probably that's the only comment I want to make. There is another meaning of framing that arises in quantum invariants and so on. That's not relevant here. This is much or it is meant to. Okay. So how many of you have seen or worked with Kirby calculus before? Okay, that's good. So those of you who haven't, talk to those who just raised their hands. I'm half joking actually. Because we'll see Kirby calculus. And my goal is to give you gentle introduction to Kirby calculus. So if you haven't worked with Kirby moves before, you will walk out of this mini course actually fairly comfortable, I hope, a bit with what they are. So this is our first encounter, but we'll see more. But the reason I asked this question is I want to state yet another theorem, and then I'll give you a small homework. So this theorem, in some sense, is going to be the homework. And by the way, here a small digression on my terminology. I'll give several versions of the problem sets. The ones which are fairly straightforward given the material presented on the board, I'll call homeworks. Those which I'll also give you problems that don't have solution anywhere yet. And if you solve them, it's actually a reasonable research problem. So I would suggest write a paper. So those I'll call problems. So my nomenclature is going to be homework, something very doable, instructive. You probably benefit by doing it. You'll understand material better and so on. But by problem, I'll refer to actual research problem because this topic that I'm presenting is sort of 5 years old. It's old enough where by now there are many theorems, even formally verified and lean and so on and so forth. But also there are lots of cutting edge research questions. And I don't want to hide those from you. In fact, I hope that you'll be able to contribute to this research, and I'll give you a lot of material to work with. So you can maybe make teams and so on. But to separate those harder questions to which I don't know the answer and would be very desirable from easier ones, I'll call easier homeworks and harder ones problems. There will be a third group, like homework with a star is a homework which is slightly harder. So this one will be actually homework with a star. So it's not quite research project. I wouldn't necessarily recommend writing a paper if you finish it, but it's also not as easy as usual. Anyway, so this theorem is says that the same is true, namely you can construct any closed-oriented connected three-manifold by surgery on so-called homogeneous braid link. So this is something that will be useful to us later. So proof or hint for this homework, proof hint is use Kirby calculus. In this example, for instance, I put a star on this homework problem because it's kind of unfair for me to assume that you know Kirby calculus when I didn't tell you what this are. So everything that's really going to be based on material in class will be honest homework. This one is sort of cheating on my part. So that's why I put a star here. But the theorem is good to record. Yes. Yeah, that's what I'm going to explain. So this theorem is good to report because this will come up later. And it's important to know that here what happened is that the simplest theorem is that you can start with a link decorated by any surgery coefficients, rational numbers, and then theorem simplifies it for you to integral ones. So it's like a stronger statement, that's nicer. So this one does something similar, but it reduces the set of links that we use to the so-called homogeneous braid links. And still holds in a way that, yes, we can access every three-manifold in the world. By homogeneous, we mean the following. So nodes and links can be constructed from braids. So what is a braid? I'll call it beta. And braid is a combination of, so you can think of a sequence of strands running from bottom to top. And at various points they can cross. So we allow to introduce various types of processing, such as this one, for instance, or this one here, and so on and so forth. And then what we do, we basically close up open bottom, and that's how we construct, that's one way to construct knots and links from braid presentation. So this piece, non-trivial piece, is usually called braid. So homogeneous refers to the following, that in a slot I, for example, slot I here, we can apply two types of one would say generators of the braid group, or crossing, over crossings and under crossings. We can cross this way or that way. And homogeneous condition refers to the fact that in the slot I, we can choose whatever we like, but only one time. So for instance, if I already use this one here, I cannot introduce another one which would look like this one. That would be forbidden. Okay, that wouldn't be homogeneous. So homogeneous would be where I do the same kind, namely this one, and I can do as many as I want. In the slots I and J, they don't have to be correlated, but it's important that I'm consistent. That in every slot I use only one type. If you're familiar with braid group generators, only sigma or sigma inverse, sigma I or sigma I inverse, and nothing else. Okay, so I don't mix them. So not mixing them is what qualifies as homogeneous braid. And the corresponding knots and links are such. So this is pretty generic condition. So it's actually hard to find knots and links which don't have homogeneous braid presentation. So under 10 crossings, you'll be out of luck more or less. So yeah, you have to go to a very high number of crossings, and maybe that's how you can suspect that yes, any three manifold can be obtained from surgery on such.
So I could ask, just to make sure I understood, so if you look at this, so a slot is sort of something in between two things, that between two strands,
Yeah.
right? You look there and you see where there's consistently an overcrossing or consistently an undercrossing, then it's homogeneous.
Exactly. And in slot 2, it could be over, in slot 5 could be under, so there is no relation, no rules how they should be, but it's important that in slot 5, we use only under, for instance, and then nothing, no overs. That's called homogeneous. So this is slightly stronger version of this theorem. And again, if you have synchrotron calculus, that's actually good exercise. And then I do encourage you to do it. So this is formal introduction to three manifolds, and it's very strong. It says basically you can obtain any three manifold in this way, so that's good. Let's actually make it slightly less formal. So I'm gonna draw sort of Venn diagram for you. So three manifolds. What do they look like? There is one particular class which is nice, and again, in this first lecture, I'll try to take advantage of this introduction to introduce notations. So they're called Briesborn spheres. So they're usually denoted by sigma PQR. That's very standard notation in the literature, where PQ and R stand for three relatively prime numbers. Relatively prime, typically positive integers. But for me, I cannot use Q because I told you that Q will appear in every talk. It's very sacred. So Q is taken. So I don't want to cause any confusion. So there is no way I can call this Q anymore. So I'll do the best possible thing that comes to mind. I'll call it P1, P2, P3. Where P is not necessarily prime, just relatively prime numbers. P1 can be a prime, but P2 can be 2 to the power of 40. That's what. So what are these Briesborn spheres? That's actually fairly easy to describe, and you don't need all this machinery. But unfortunately, this is pretty much the only class where you don't need this machinery, and it's extremely tiny. So you can consider, if you like, complex analysis or algebraic geometry, a hypersurface. You can take complex variables x, y, and z, and hypersurface x to the power of p1 plus y to the power of p2 plus z to the power of p3 equals 0 or constant. So this will be union C3. So we have three complex variables X, Y, and Z. And intersected with a big sphere. So here, C3 is a real six-dimensional space. You can imagine a large or unit radius that actually doesn't matter sphere in there, for instance, x squared plus y squared plus z squared equals 1. And this is a 5-sphere when intersected with codimension 2, real codimension 2 locus defined by this hypersurface. It cuts out something 3-dimensional, and this 3-dimensional is this manifold. So I'll put this definition column. That's how we define gray squared spheres. So now you know how for 3 relatively prime numbers construct explicitly bunch of spheres. So they're all going to be homology spheres, and Poincare sphere, which was subject of Poincare misleading, but then led to interesting conjecture and so on, is in that family. And Brieskorn and others, Milner worked on it, and yeah, so this is a very nice family. So this is kind of good, very tame family of simulation. So it belongs to a larger family, so-called Seifert manifolds. And Seifert manifolds are basically circle bundles over genus G surface, where you allow a circle to have, where you allow any number of singular fibers and then of various kinds. So a circle can do some weird things. So I'll probably skip this family for most of the time because this is tiny in the world of free manifolds. This is sort of still a bit special. So the next family that's less special is called plumbed free manifolds. Plumbed manifolds, or sometimes called plumbings. I guess that's an affectionate way of referring to them. So that's a much bigger family. In fact, it's as big that if I am asked to enlarge this class further, I don't know any intermediate class between this and all manifolds. So therefore, in the next layer, I'll just say all. But from the perspective of all, plumbed are still reasonably special, but again, this is humongous. And I should emphasize that each of these classes, of course, is infinite. So even the simplest, most boring one, this Brieskorn spheres, is labeled by infinite collection, infinite triple set of triples of relatively prime numbers.
You know that those two classes are distinct.
Yes. There are examples of Seifert manifolds which are not Brieskorn spheres. There are examples of Planck manifolds which are not Seifert.
I mean, between all and plumbed.
And there are examples of all manifolds which are not. Yeah, that's a very good question. In fact, I didn't plan it as the homework, but it actually may be a good exercise with a star. So maybe a little bit of further notation, since we're going to work with these manifolds and construct their invariants. What are these one manifolds? So I'll denote a decorated graph. Let's introduce a decorated graph. Probably if I need notation for it, I'll just call this object gamma. Or equivalently, we can use notation forming graph. It's a graph. In particular, it has a set of vertices. I'll call this vert, and set of edges. I'll call this edges. It's like the Python definition, where you can create a class, plumbing graphs. But importantly, with additional data, so that's why it's decorated. With a function, I'll call it A, that sends that assigns to vertices integer numbers. So in practice, what this means is that I have a graph, say something like this. You can imagine a graph of some social network or linking diagram or something like that, where to vertices we assign integer numbers. For example, +1, minus 10,000, and 1, 3, 45, and so on and so forth. So these are various integers, and I'll call this integers AI. With artificial intelligence, just AI. So this is going to be a representation of a three manifold, and the corresponding manifold will call. So I'll just say that there will be a notation M gamma, where M stands for manifold and gamma stands for this decorated graph. And you can ask, what does it mean to have manifolds labeled by this graph? So these are going to be manifolds which are still constructed using this very general theorem of Recursion laws, except the following. We can notice that if in this statement of the theorem, we only have unknotted circles like this component, and not anything knotted like a trefoil, we can actually reduce the data of this link, which is like knot theory and so on, to just boring combinatorics that we can explain to high school students. And that's going to be combinatorics of the graph. In other words, if I see a graph, it actually secretly hides the information of a link in the following way. You take a node of the graph, the vertex of the graph, and replace it with a knotted circle. Every time you have two vertices, so for example, here I have two, they have to be linked like a hook link. And important point is that individually they cannot have any knottedness. They cannot be tangled in a non-trivial way, like a, say, trefoil knot, for instance. So here in this diagram, I have, for example, these three guys. So it will be a picture like this, then this will connect to something else, and so on and so forth.
Sergei, do you allow multiple edges and loops, self-loops and stuff?
You can, yeah, you can. So in fact, right, so there are, yeah, let me finish with this, I'll come back to a generalization. Yeah.
Sure, in this three element vertex, why we don't loop like these two around each other?
That's the rule, just because we have to follow the traffic rules. So the rule is that every time we have an edge, just these guys are linked. So we don't think about anything more sophisticated.
Yeah, but 3 and 4 to 5 should be also linked, but they're not.
Yeah, so let me call this with framing or surgery coefficient 2. So for example, there will be labels, surgery coefficients 1, 2, 3, just so we understand what's going on. And this one will be surgery coefficient 45. So what I'm saying is that the data of this graph gives me the data of the surgery, or sometimes called Kirby diagram. So I can probably start using proper name. This is Kirby diagram for my three manifold. And it consists only of unknots, which are linked only in the simplest possible way as a hook link. I can reduce one to the other. So it will get in trouble if I try to use as a Kirby diagram Borromean rings, for example, or use some kind of triple linking number, something more sophisticated. Then I'll get in trouble with one-to-one dictionary. But if every individual component is just a knot, unknotted circle, and if they're only linked using this simplest possible Hopf-link relation, then for example, the central guy, this node which has connection to 3 other friends, is linked like a Hopf-link to this, despite my poor drawing, and to that one. So then it's 1-to-1.
It seems there are 2 ways to link to unknown. So
In
there's
3
a
dimensions, not really.
yeah.
So,
But what if you have a loop in your graph?
yeah, so that brings me to further questions. So, in general, there can be several things. So first of all, there could be there is actually analog of multiple edges. There is also a possibility of having a loop on a graph. And in that case, actually, how the number of twists will be important. But, and then there are various other generalizations. Actually, each vertex has to be labeled by 2 integers, one of which is Sergei coefficient in my presentation. There is yet another generalization where the second label is genus, GI. So for simplicity, again, this is supposed to be school, no, not super advanced workshop. So I'll put this to 0. So I'll suppress them for most of our discussion. Multiple edges and loops in the graph, we'll come back to it. But again, I suggest we suppress them for initial discussion unless we want to complicate our life from the start. So if you want that, I'm happy to do it. But if you want easier thing, we'll suppress them. Why? Because if our graph is actually a tree, there are no loops, then it's abstract. It's sitting in some abstract infinite dimensional space. So we can always untwist. So if you introduce these twists between the knots, we can always untwist them if it's a tree. So there will be only a need to consider such twists if we have a loop, and there is actually a very good reason for it. In topology, it arises from spin structures, but I want to suppress this for the start. I mean, we'll come back to it. It's a very delicious part of the subject, but it's definitely maybe too early for it. Yeah.
You usually allow for loops on the same vertex.
Loops on the same vertex?
Yes. So you're starting at 3, ending 3. Instead of a loop that running through the edges, but like an edge that starts in the ends in the same vertex.
Oh, you mean something like this?
Or no, that never happens, even in the generalization.
Well, I'm not, in generalization, the closest would be this probably, or having loops in general. I mean, there will be various equivalences, so it will be natural to put another vertex here to kind of resolve it, so we'll make it that bigger. But according to this rule, which relates Kirby diagrams and not decorated by Sergei coefficients, and this graphs, I wouldn't know what this means. Because see, vertex represents a knot. And vertex connected by an edge to another vertex represents a knot linked to another knot like a Hopf link. So now if you say, let's have an edge which represents Hopf type linking with itself, so what does it mean? You have to answer that question. I don't know. It's a.
So maybe, can I comment on this? So there are like 2 different topological construction. One is this dense surgery. And the other one is like that with the original plumbing, which is taking circle bundles over surfaces and then gluing them together. So then if you think of it in this, you can also have a loop from the vertex to itself. But then the correspondence between these links becomes a little bit more complicated.
Okay, so is this okay so far? So then we already have our territory for constructing 3 manifolds and notation for some of the classes. I won't need any more technology most of the time. So then little things that we need, I'll introduce along the way. But in terms of how we represent 3 manifolds, this is probably in some sense the heaviest part. We started a few minutes late, so I'll use last 10 minutes to give you another definition. Yes.
Sure. So there you're saying, I think the free manifold, obtained by surgery on this, that's your definition.
Yeah, that's exactly. So that's why I didn't write anything here, because if I were to write, it would be lots of words, but it is, I just want to record that we define an object.
So-
By gamma. So if you actually don't like three manifolds, not everybody raised questions to this three manifold. Not everybody raised hands to this three manifold question. Then think about graphs. So that's why I'm presenting it as combinatorial gadgets. Like, think about graphs if you don't like three.
It seems that M gamma doesn't really depend on decoration, right?
No, it does. It's because these coefficients, 1, 2, 3, and so on, these are my surgery coefficients. So these are my surgery coefficients, so it does. So this decoration or surgery data, they're all synonymous terms, are part of the definition of gamma. And free manifold does that.
Plumbing graph corresponding to a Briscoe sphere.
Okay, so that's a very good question, and maybe I should suggest some homeworks related to that. So. Yeah, let's get back to this. That's a very good question, but so I mean, Gunther, as to those of you who work with this and or have some expertise, involves there is it's not a nice simple answer where I can just write a graph and that's it. Because it will involve continued fractions and all kinds of things. But there are several examples that, so yeah, there are several examples that I would to consider. So that would be probably honest homework. So work out, for instance, simplest possible graph consists of only one vertex, right? So that's not much of a graph, but it is a graph. It fits them and it's part of the definition. So if I put here integer coefficient a, okay, and it can be any integer. But what is the answer for three manifold for different values of a? M of this. And I promise you, you know this manifold, or in fact, there's a whole family of manifolds. It's in family. Even if you didn't have much experience with three manifold topology, you know the names of them. So just attach names to values of things. That's enough. So right here, I wanted to introduce a couple of definitions before we run out of time. So I will do a minute. With the permission of generous care. Give me a thumbs up. So first, let's introduce adjacency metrics. I'm called linking metrics. Now, given the data of such graph, for a while we're going to label our manifolds by graphs because it's fun, because it's combinatorial, and because if you work with antigradients, you can tell them the story. They usually like graphs. So every time you see an edge between vertices I and j, you'll put an adjacency matrix 1 as off diagonal element. So if ij belongs to the set of edges, we'll put ai if I equals to j. Because if I equals to j as we discussed, I don't know what it means to have linking, self-linking and so on. That's kind of frustrated. But luckily we have set of numbers which are perfect for this. So we'll just put this integer values, the Sergei coefficients on a diagonal where this is sort of confusing or conflicting. And we'll put 0 otherwise. So any questions on this definition? So then next and the last for today is definition of UQ invariant for this manifolds. So UQ SL2 invariant of M gamma. By the way, here I should make a comment. So this, before I go there. So we construct, given such decorated graphs, three manifolds using this connection or dictionary to Sergei representation. And it's natural to ask, what is H1 of this three manifold in terms of our combinatorial data? So now that I introduced the adjacency matrix Q, this is actually a co-kernel of Q. Okay. So Q stands for quadratic form. I don't know if I'm going to use any other Q, but I think that's fine for now. So in particular, when Q has determinant which is non-zero, then this manifold is rational homologous here. It doesn't have Betti number. So remark is that it's rational homologous here when determinant of this quadratic form is non-zero. So let's assume that's the case, simply because relaxing this condition is the same thing actually as creating loops in a graph. It basically makes our three manifold non-simply connected in a way, not just having cyclic factors in H1, but rather having Z in H1. So our beta number will jump. And as we said, we'll discuss loops later. So they're kind of interrelated.
And right is equal to 0, right, for the Betti number there.
Oh, yes. Sorry, thank you. Right, and moreover, let's assume more precisely Q to be negative definite. So it's all eigenvalues are negative, or to some technical reason that will actually, that's a stronger condition that will guarantee this.
Just as a notational thing, Q is depending on gamma, so it's sort of like Q sub gamma, just like we have M sub gamma.
Yes, yeah. So Q sub gamma. There was another question.
Oh yeah, I was gonna ask, is being rational and rational homologies here, that's because you're taking rational coefficients.
No, I like to work with integer coefficients. So rational is no, just a term. That means the Betti number is zero.
As the same.
But I actually do care about H1 over integers. So for me, unless specified otherwise, actually I work over integers. I love torsion. I love spin structures. I love anything like Z2 is so cool. Z3 is even better. Z13. Okay, so let me finish with outline and then we'll continue next time, but I want to get to something quantum. This was just topological background, so this is something for you to play with. And I promise it won't take more than this board. So what they'll do will associate to a three-manifold M gamma, a quantum invariant, which will depend, of course, on M gamma. It will also depend on Q, so that's going to be our quantum parameter. And remember, everything is Q is assumed to be generic inside the unit disk, and it may depend on other things that I'll specify later. So you can define it in many different ways, and I'll give you many different ways in the second lecture, but first I want to give you an idea. One definition is that you take product over I, which runs in a set of vertices of complex integrals. So maybe J xj over 2 pi I xj, where we'll take one complex variable xj for every vertex in the graph. For instance, if my graph has 1 million vertices, then yes, that's my fate. I have to do 1 million fold integral. Yes.
It's the VP difference of value.
Yes. Yeah. I was going to mention it briefly as I talk about the contour. So there will be some integrand which I have to specify. So I have to tell you a couple of things. First of all, what's the integrand? I'll come back to this in a second, but since you asked, let's address the contour. So we'll be integrating in a huge space, basically a complex space of dimension equal to number of vertices in a graph. And for each vertex, we'll have complex variable xj. J labels the vertex. And for each variable, the integration contour will be on a unit circle. But if we run into some issues in the integrand, then we take principal value. Although in practice, this will never happen. This will happen rarely, so just to be absolutely precise, and then the rest of the integrand will be arranged in the following way. It will be some universal piece associated to every vertex as part of this product. Then we'll have product over edges, ij and set of edges, and some universal piece for every edge. And then we'll top of things with a theta function associated with the quadratic form Q that we already introduced. So theta function is what you think it is. It's a sum over a lattice of the same dimension as number of vertices. And then you have xi's, xj's raised to linear power of the lattice vector and Q raised to quadratic power of the lattice vector. So it's basically a theta function for that lattice. That's why it was convenient to assume that quadratic form is negative definite. So I have to tell you what are these ingredients for every vertex and every edge. And the rule is following, that if you see vertex in your graph labeled by some vertex I labeled by AI, that contributes to the integrand due to the minus AI plus 3 over 4 times xi minus 1 over xi squared. So it's natural that contribution of vertex labeled by I, or sorry, J, I don't know which one I prefer to use, depends on that particular integration variable. So it's basically, it's very modular, it's like Lego. So you have pieces, and if you have in your graph some vertex, and we have its corresponding Sergei label, but also now integration variable x, it's natural that what goes into this complicated integral depends only on that particular vertex. So it's going to be kind of local with respect to graph structure. So if you like lattice models, this is maybe very much like the lattice model. It's an integral. And if you see an edge, it's an edge that connects vertices I and j, then that will contribute a factor xi minus 1 over xi inverse, xj minus 1 over xj inverse. So if you think about it, all this, this may look complicated, and the way I broke it is that it's modular, so you can break it into vertices and edges. But you can just, because this factor is factorized, so it doesn't involve non-trivial interaction of xi and xj. You can basically write it as product over I in vertices of gamma xi minus 1 over xi to the power 2 minus degree of vertex I, where degree means valency, how many edges it has coming or fine. So that's the definition. And as a homework, which probably is more relevant for tomorrow, but you can already start sort of thinking about it, and tomorrow I'll help you to finish it, is basically compute this invariant for the following gamma. So everything is going to be labeled by -2, very much like in the thinking diagram of E8 or A or exceptional group. So 1, 2, so here I have -2, but then I'll have a funny rule. So here I'll switch to -3 and then continue with -2s. And we'll have, let's say, n of this. So everything is going to be labeled by -2, except one fellow which has 4 -2s between trivalent vertex and this. Okay. So this looks very esoteric. It actually illustrates example of a graph with lots of vertices. So it will force you to think, is this really as complicated as it looks? Of course, the answer is no. It's much simpler, and that's something that we'll discuss next time. But this is actually the homework that I do encourage you to do as much as other homeworks without the stuff. Yeah.
So is there a particular number of -2s between the offshoot and the -3?
Yeah, there is a particular number. It's important. It's 4 of them.
Oh, okay, so it's as you
So
go.
unless I made any mistakes.
Okay, so you're not implying that there's some arbitrary number.
No, it's not arbitrary. Of course, again, so I'm trying to illustrate with this homework several things at once. So that's why it's chosen carefully. It illustrates that, yes, you can play with all these integers. In fact, if you want, that would be star. So explore the deviation where you have 3 in between prevalent vertex on this -3 or some other integers as Sergei coefficient. So that's going to be fun. But this particular family will be useful to us in other contexts. All right, so I'm done. I apologize for running 30 minutes late. So thank you for your attention.
Quick question. Yeah.
Is the formula related to the failed combination?
Sorry?
Is the formula related to the failed combination?
Yes, it is related. So the question was if this formula related to Weil denominator form. It is because there is actually group theory or representation theory hiding. So this x minus x inverse appearing everywhere reflects the fact, in maybe not so direct, but you plotted play that we deal with SL2. So if we have SL3 and high rank gadgets, there will be a rank number of variables per vertex, and so on and so forth. But anyway, yeah, so you're anticipating vast generalization. Most of the time I'll be dealing with SL2, and that's why, yeah, some connections are apparent and you plot it. I'm not sure another question is allowed.
Maybe we'll save any other questions for the coffee break. We will resume at 11. Let's thank Sergei again.